Okay, so starting with number 1. Find the derivative, but we have to spend the time to do some cleanup before we can apply power rule to each term. Okay, so I'll go through each step. So if you want to do power rule, 3 conditions have to be met. All right, variable has to be in the numerator. Any radicals need to be rewritten with rational exponents. And then we want to expand parentheses. So that means if there's any variables that need to be together, we need to put them together. X's that are together, we need to merge them together. Any parentheses we have to resolve. Right, so looks like we can do some work with that first term. Now, I would say, product rule is second option, right? We normally don't want to do product rule unless we have to. And this is one of those problems where if we can avoid product rule, we want to avoid it, right? So always consider power rule first. And if you realize, okay, I don't want to do power rule with that problem, then you can look for other rules. But here, this is easy enough. We should be able to distribute this through and just get it cleaned up. And I don't think it's worth the trouble to go through product rule. But I'm going to do some rewrite here. X squared of x, the same thing as x to the 1/2. I'm just going to go ahead and start distributing through. It may take a couple of steps for me to get everything ready, but it's okay. We can take our time. Right? And also this fraction here, this is written in a way that is not as easy to read. So we can pull that 2/11 out. That way we can just think of every fraction as just a number in front of the variable. Feels a little bit easier to read. We don't have to stare at a number below a variable. And if a term is ready for power rule, I'm going to go ahead and rewrite it because I'm just going to wait until every term is ready. Cube root of x. Okay, so this is the one that I think some students struggle with here. How do I rewrite square root of x to the 7? Mm-hmm. Mm-hmm. Good. 7/2. 7/2. So I think a lot of students want to write 1/7. Okay, this is not 1/7. This is 7/2. Okay, so the two statements in the denominator can pull this up to the top. This becomes -7/2. So plus 5/2 x to the -7/2. Okay, we're almost ready. I think it's just this first term that needs to be rewritten. So what do we do with these two exponents if we want to merge these together? At the exponents. So 3 plus 1/2. Same thing as 6/2 plus 1/2, which is 7/2. Let's just rewrite everything so I can just. Oops. Okay, any questions so far with the cleanup stage? Extra worksheets here, you can get one. Okay, so now we're ready for power rule. So for every term, we can bring the exponent down, and then we can subtract 1 from the exponent. Seven halves minus 1 is the same thing as 7 halves minus 2 over 2. Power rule with whole numbers is a little bit easier. X squared becomes 2x to the first power. What does 4 pi x become?
Just 4 pi.
Good, just 4 pi. What does 5 pi to this fourth become?
0.
Good, 0, right? It's a constant. We don't want to treat any symbol as a variable, right? That's not a variable. We don't do 20 pi to the third, right? It's just 0. Bring down the 1/3, subtract 1 from the exponent. So 1/3 minus 3 over 3 is negative 2/3. Bring the negative 7 halves down in front, subtract 1 from the exponent. Okay, what's negative 7 halves minus 1?
Negative
9 over 2, right? So take the time, right? Sometimes students forget about that negative bit, and they want to do 5 halves, right? So 7 over 2 minus 2 over 2 is negative 9 over 2. Okay, so the calculus is done. The rest of this is just doing cleanup.
Put that in radical form on the denominator.
You can, yeah, you can leave things in radical form. You can have this as square root of x to the 9th. But just no negative exponents in the answer. Any other questions with number 1? Yeah.
Like when you move it to the front and then you're trying to get the exponent again, what do you subtract that?
Subtract 1.
Okay.
Yeah. But sometimes it looks a little different because we got to subtract 1 with a common denominator. So it could be 2 over 2, it could be 3 over 3. But we always subtract 1. Yeah, subtract 1. Okay, number 2. Our function is x squared over x minus 1. Find the derivative. So to find the derivative, we have no choice but to use what? Quotient rule, right? We cannot freelance on this derivative. We can't say 2x over 1, right? It's not as easy as that. We can't just do power rule for both and just leave it like that. I mean, this is not the derivative. Okay, so we got to go through quotient rule. F prime g minus f g prime all over g squared. Okay, f prime is 2x. Back to g function. Back to f. G prime is 1. All over denominator squared. Let's do some cleanup with the derivative. Now, can we ever do this? Take the x minus ones out. No, okay. That minus sign is preventing us from able to cancel anything out. So what we want to do is we really just want to focus on trying to get that numerator cleaned up. Okay, so there's my derivative. Again, the whole purpose of the derivative is to talk about what is the steepness of every point on the original graph, right? So any point on the original graph that has a slope, I can figure out what that steepness is by just inserting and giving it an x value, right? So we have our function, we have our derivative. Now we should be able to gather all the information that we need to create the tangent line equation. So tangent line equation, we need order pair and we need slope. So to find order pair, we're simply going to insert -1 into the original function to get the y value. Okay, so f of -1. -1/2. To find the slope comes from the derivative. It's inserted into the derivative function. Okay, so we have our order pair, we have our slope. Now we can put it into point slope form. Okay, any questions through this process? Number 3. So if you look at number 3, it says find the derivative of the function. Now, look at how this is set up. We have 2 options available to us. What's one way that we can work towards finding the derivative? Power rule, right? But power rule require having to expand everything out, which we can do, but you just have to, it's more terms than just 2 binomials, right? So it'll take a little bit longer, but that's perfectly fine. You can do it that way. Another option is product rule. So I'm going to go through product rule just for to show that step, but you can definitely expand everything out, rely on power rule, and that's sufficient as well, okay? The answers may look a little different, but both processes are perfectly legitimate. Okay, so for number 3, I just rewrote the problem to get it ready for to get those rational exponents taken care of. But here I can now go through product rule. Let my first be F, let my second be G, and it's going to go through. Okay, so there's my form for product rule. I'm just have to fill in that space with whatever is asking, either the derivative or the original expression. So F prime, just have to go through power rule for both of these and put it in there. G function, no changes. Back to the F function. Okay, G prime. What does 2x become? 2. What does 5 pi cube become?
0.
Good. What does 7 become? 0 as well. So there's only a 2 left over there. I'm not going to ask you to clean up. This is perfectly fine. But if I ask you what is the slope at a point, then you would insert 1 or 2, whatever the number is, in the derivative, and you can leave your answer unsimplified. Okay. Okay. Any questions with the first page? Okay, second page.
We'll just leave it like that. You like this? Yeah. I'm gonna ask.
Okay, number 4. Particle moves along the x-axis in meters so that at times t is greater than or equal to 0 seconds. Okay, so pay attention to the units. Its position is given by x of t. So that means if I enter in a t value in return, it will give me a number, and that number will correspond with where this object is on the x-axis. Find the velocity acceleration function. So we simply take the first derivative and the second derivative. Yeah, velocity is always the first derivative of position. Acceleration is always the second derivative of position.
They gave us velocity.
Mhm.
And like, could I like go back?
Right, this semester, we don't know how to go backwards. So if you're given just velocity, you're never going to be expected to figure out what the position is. Not until second semester. So if you're just given velocity, that means you're only working from velocity down. Yeah. Okay, so velocity function. Looks like every term is set up and ready for power rule, so we can go directly into power rule. There's no need for cleanup. So there's my velocity function. Acceleration is my second derivative. 3t squared becomes 6t. Negative 60 becomes minus 6. Negative 9 goes to 0. Okay, easy enough, right? Any questions? Okay, B and C are pretty straightforward. Find the velocity at 2, find the acceleration at 4. We're just simply taking the t value that they have for us and inserting it into each equation, each formula. Okay, 3 times 4 is 12. 12 minus 12 is 0. 0 minus 9 is negative 9. What's the unit of measure here? Right, go back, read the problem. Don't assume that just because you're seeing a unit for a lot of problems, that it's going to be always that, right? Go back, read the problem carefully, and adjust to whatever the unit is given in the problem. Okay, what's the acceleration at 4 seconds? 4 in for t. $18. Okay, what's the unit of measure? Good, meters per second or meters per second. Okay. At what time does the particle change directions? Justify with reasoning. So anytime we're asked about where the object changed direction, whether it's moving left, whether it's moving right, I think the easiest way to do that is to create your velocity sign line. That way you can see a visual idea as to what the object is doing in terms of its motion at any moment in time. So we'll create a velocity sign line here. But let's see, before we do that, we first have to find where the particle is at what? Yeah. In other words, when velocity is equal to 0. All right, that's going to help us create our separations in our subinterval. So we're going to set our velocity equal to 0. I'm just going to go up here and do some cleanup here. Second factor. 3 out. Okay, so just getting all factors, I can solve for t. Multiplies to be -3, adds up to be -2. That's -3 and 1. Solve for t, and I get 3 and -1. So think about your velocity sign line here. What is the restriction based off of the original problem here?
You cannot be left.
Yeah, we're only looking at values for t that's greater than or equal to 0. So that means anything that's to the left of 0, even if it's a point that we found, is not going to live on our sign line. Right? So that means what's removed then? -1, right? The -1 is not part of our domain, so we're not going to include that in our timeline. Okay, we want to populate the rest of the sign line, and we want to be able to identify the direction of motion in each of those subintervals. We know that there's only going to be two directions of motion because we have two subintervals, so everything in this region will be going in the same direction. Everything in this region will be going in the same direction, either left or right. So I can choose test points. I'm going to choose 1 between 0 and 3. You can choose 2 as well if you want. You can choose any number to the right of 3. Bigger that, the easier, smaller the number, the easier to plug in. So I'm going to insert into the factored form of my velocity function. That's the easiest one for me to get the information that I need. I only care whether it's positive or negative. Okay, so 1 will go in for t. I don't care about this 3. That 3 is not going to affect the sign of my velocity. So I'm just looking at the parentheses here. Okay, so 1 minus 3, that's what? Positive or negative? Negative, okay. And then 1 plus 1 is positive. So negative times positive is negative. So we know that in this time interval, this object is continually moving to the left. All right, 4 in for t. 4 minus 3 is positive. 4 plus 1 is positive. So this object is going to end up turning around at 3. It's going to stop at 3, turn around, and move to the right continually. Now, as soon as you do this, go ahead and cross out these test numbers because you're never going to use these again. Okay. I see sometimes students, they want to involve these numbers in future statements about moving left or moving right. Okay. The only purpose that we have these numbers is just to get these signs to show up. After that, we don't care about those numbers anymore. So that means if there's any statements about interval, you're only going to involve 0, 3, and infinity. That's it. Not going to involve any test numbers in your statements. So it says, at what time does the particle change direction? We see that there's a change in direction at t equals 3 because there's a sign change. So okay, at t equals 0, is the particle moving left or right? So that means we can just insert 0 into a velocity function and see what sign that gives us. So 0 in for velocity. All right, let me extend part E for a little bit. Let's say the problem says, when is the particle moving left or when is the particle moving right? So I'm just going to add that here. So if it's asking for moving left, you would say what? With brackets or parentheses? Brackets around 0 because it's actually already moving, right? It's already moving when the timer starts. Parentheses around the 3 because it stops at 3. And then if it's asking for justification, you would say because v of t is less than 0. If it's asking for moving right, you would say, say it again. Good, 3 to infinity, everything parentheses here, right? 3 is, it stops, infinity will never be reached, so that's parentheses as well. because velocity is greater than 0. Okay, so that way you can see all the possibilities that the problem can ask. It can ask you, when is velocity at rest? You can find that by setting velocity equal to 0. Changing direction, looking at your velocity sign line, and then interval moving left. You look at all the intervals where there is a negative. Moving right, all the interval where you see a positive. And then your justification would look like this, because velocity is less than 0 for moving left, and because velocity is greater than 0 for moving right. Okay, part F, find the average velocity. Okay, so this gives students trouble here. What's the definition of average velocity? Good. Change in position over change in time. We do not touch velocity function through this process. Okay, so formula will look like this: x of 3 minus x of 1 over 3 minus 1. So that's the formula you're going to use. Okay. X of 1 and x of 3, you're just going to insert 1 and 3 into the position function, find the locations, and then just simply go through that formula. So I'm just inserting 3 into the function here and finding the position, inserting 1 into the position function, and for t value to get its position. Gather those specific locations. Now I'm just going to put into the formula. So negative 25 plus 9, negative 16 over 2, be negative 8. All right, what's our unit of measure here? Give me a second. Okay, so even though we didn't touch the velocity function, we are still doing a velocity calculation here. So our unit will still be how we would expect with, with velocity. Okay, displacement. Displacement is simply the change in position. Okay. So it's similar to average velocity, but then just without the denominator. It's final position minus initial position. And that's it. Okay, so if it's negative, then you leave it negative. If it's positive, you leave it positive. Don't make any adjustment. Whatever you get, that's your displacement. So 4 into the position function will give me negative 18.
Putting it back to the original.
Good, into the original, yeah. Into the original position function. X of 1 is negative 9. So negative 18 plus 9 is negative 9. What's the unit for displacement?
Meters.
Just meters, yeah. It's just how far, where are you in relation to your starting point? So here, that just means between 1 and 4, he's 9 meters back from where he started. Okay, part H, what's the total distance? Total distance is similar to displacement. We're still going to use initial position and final position, but there could be an additional location that we're looking at. And we have to consider, so this total distance, we have to consider, is there a time period between our initial and final where there is a direction change? Because if there's a direction change, then all of a sudden we got to keep track of his motion forwards and backwards. So the way we determine that is we look at our velocity sign line. Does he change direction somewhere between 1 and 4? Does. So we have to also include his location at 3. So we have to include his location at 3. So initially, same information. X of 1 is -9. X of 4 is -18. So we have to do the additional step of finding his location at 3. So insert 3 into the position function. So 3 cubed minus 3 times 3 squared minus 9 times 3 plus 2. And all that gives us -25. So how do we use these numbers to get to our total distance? Okay, so don't look at 1, 3, and 4. Okay, that's not going to help you with anything. You're just looking at -9, -25, -18. Now think about these numbers like you would if you're walking along a number line. Okay, so I'm just going to put those numbers down here. -25 is the furthest left. -18 is somewhere to the right. -9 is further to the right. Okay, so imagine you're walking from -9 to -25. And all you're doing is you're just counting your steps. Okay? Each step, you're going to make 1 increment towards -25. Okay. And then you're going to turn around. You're going to continue to count your steps, -25 to -18. You don't care about which direction you're moving. You're just keeping a running total in your head and just keep on adding your steps together. So between -9 and -25, how many steps would you have taken? 16. You do -25 minus -9. You make it a -16, but again, you're just counting steps. So keep that as a positive number. So you walked 16 steps to get from -9 to -25. Good. You keep that number in your head. And then from -25 to -18, how many steps would you have taken there? 7, right? So -25 minus -18, that's any negative number, you just convert it to a positive number. So you took 16 steps going left, you took 7 steps going right, but again, you're just counting your steps, so everything is positive. So what's the total distance? 23, 16 plus 7. So displacement can be negative, but total distance is always positive. Okay. Finally, last two here. Is velocity increasing or decreasing? So this word sometimes trips students up here. Do we look at the velocity function? No, we look at just acceleration, because this increase decrease is not talking about velocity, it's talking about the rate of change of velocity, which is simply just acceleration. So this is the rate of change of velocity. So we only care about acceleration. So we go to acceleration, we find the acceleration at 2. Insert 2 in for acceleration, we get positive 6, right? 12 minus 6 is 6. That's the only thing that we need to make our conclusion. Because we have a positive acceleration, that means velocity is what? Increasing. If we get a negative acceleration, that means velocity is decreasing. Yep. Okay, part J, wording is very similar, but instead of velocity increasing, decreasing, now it is to speed increasing, decreasing. We have a completely different set of method to do that. So how do we determine increasing or decreasing speed? Good. We look at velocity, we look at acceleration at those moments in time, and we compare their signs. Okay, if their signs are both the same, speed is what? Increasing. If one is positive and the other is negative, then speed is decreasing. Yeah. So we find velocity at 4, which is 15. We find the acceleration at 4, which is 18. They're both the same signs. So therefore, we can conclude that speed is increasing since velocity and acceleration have the same signs.
If they were different, would you have them together, or would you just say that positive, negative?
If they're different, let's say velocity was -15 and acceleration was positive 18, then you can just say speed is decreasing because velocity and acceleration have opposite signs. Yeah. So we don't really care about these numbers. We only care about what the signs are. That's right. If they're both negative, then speed is still increasing. Speed is still increasing if they're both negative.
So for like this one, it has to find the slope. Do we do the same thing we normally would do if it was the fraction term we had?
Yeah. So here, you find the derivative, and then you just insert one into the derivative. And you do your answer and simplify it.
Oh, I think that was the slope. Okay.
What's your name? Would you just put that in place of the dy over
This says find the derivative of the function as x equals 1. Just replace all the x equals 1 with nothing else.
For this part of the average velocity and time, do you just do, how did we get 3 minus 1 again? Because the signs are different. Are you supposed to add these two together?
Oh, no. This is not related to that.
Okay, so just the
Just that
point.
one.
So
This
just
is
take,
not- yeah, it's
so
a
just take the
coincidence.
y point minus the x. Okay, thank you.
So for this one, how do we know when to stop? Like, why wouldn't we multiply these terms?
You could, but I'm not gonna ask you to do. Yeah. The problem that's messy, I want to specify to, simplify. If you have the way that you improve it, but a form like this, I'll be okay with you leaving your answer simplified.
So for one where it says to find the derivative and we're using product rule, I just have to leave it here unless you specify simplify it. Thank you.
Okay.
Average velocity is just changes lifting over changing time. Oh, average velocity, you don't touch velocity.
I guess I forgot to change it to X. I figured that out this morning. Average acceleration questions.
No, but average acceleration would be change in velocity over change in time.
Okay, gotcha. Okay, so.
But you're just using position for average velocity.
Gotcha. Okay, and then I have, this one. So when you do the displacement, we always do the first, last, and then wherever it changes.
Exactly. You rely on the sign line to help you determine if there's any number. It's possible that there's none, but if there is, you gotta make sure you include that.
Okay, thank you. So for displacement, we also have to include this, or it's only for
Sorry. Displacement is just final and initial. So we're on the distance, and you include.
that in this.
Sorry. Displacement, you're just doing final position minus this. We don't care about anything else.
I guess
Distance,
it didn't matter though, because that's that.
uh,
Or was that just like a fluke that it equaled that?
yeah, I would not include.
Don't include the middle
Don't include
thing
the
in
middle.
displacement? Okay, so
Distance, yeah, good thing you brought that. So distance, then you gotta look at your sign line to see if there's a change in direction. If there's a change in direction, you gotta include that point in your calculation.
okay, you want the sign line for?
No, you don't need it, but I think visually it helps to just visualize you walking back and forth
Okay.
and counting your steps.
Okay, and if there wasn't like a change in direction?
Then these numbers will be the same. Your displacement distance will be the exact same because you're just counting the steps from one point to the end. You're not changing the direction.
That's good. So, I wanted to ask for like average, starting to get on here, we started using the original. How do you know when to use like the original, not like velocity?
So average velocity is defined as change in position over change in time. So if we understand that definition, then we're not going to touch velocity. Displacement is also just the position, and then distance is also just the position, but we do need a velocity sign to bring that potential.
And then
Okay.
when it asks for increase and decrease, we really don't even worry about the velocity. It's like,
Just acceleration.
okay.
Here we got the acceleration.
When it asks for like position, like that, we use the original, and then when it's asking for like that, it's coming into like velocity.
Yeah, so the hard part is trying to figure out what do I need, right? And so yeah, continue looking over that.
Okay, awesome. Thank
Exactly.
And that, how would you justify?
You have to create a sign line. Create a sign line and actually see if there's a change in direction either side of three. Oh, that's right.
Then you don't have to do.
If it says for change direction, you will say because you need to change the sign.
And then this one, you will so we could just acceleration.
Right. If they're both positive, or if they're both positive or they're both negative, speed is equal. One is positive, the other is negative, speed is equal.
And then for this one is particle one like one times like you write the position of the and then say.
If there was no change in direction between 1 and 4, then it's the same as the same, you'll get the same number. Either way, either way, get there either way. If you slope, you would set, you would put the slope in here, and let's multiply and solve for x, and then you get the y value of y.
Okay, and if it comes out with two values, I would
Yeah,
give it both.
yeah, I got it.
So, like the sign up just like this, it's not.
You need the sign line to know that they're rotating.
Yeah, but if I set it up like
That's
that.
the answer. Well, I see.
Very slowly grade.
Okay, so I got